Okay, so let's get one thing straight. This is not your high school geometry class. Nope. We're not going to be just talking about circles and triangles. We are going on a quest to understand the fundamental shape of our universe. For thousands of years, humanity has been trying to map the very fabric of space. And trust me, it's a story that will completely change how you see, well, everything. I mean, it's pretty much the biggest question you can ask, right? And for most of human history, our number one tool for even trying to answer it has been geometry. So where does this incredible journey even begin? Well, it doesn't start with some abstract philosophy. It starts with really practical, down-to-earth problems. Things like dividing up land, building massive pyramids, and trying to navigate by the stars. And the name itself tells the whole story. In ancient Greek, geometry literally just means earth measurement. Its first job was super practical. It was just a set of rules and principles for dealing with lengths, areas, and volumes in the world right in front of us. For thousands of years, cultures from Mesopotamia to Egypt were using geometry for all sorts of practical stuff, especially construction. We found ancient texts that have formulas for building pyramids. But then the ancient Greeks came along and started asking the totally new kind of question. Not just what works, but why it works. And that led to thinkers like Pythagoras giving us the very first logical proofs for these geometric ideas. And that right there, that was the crucial shift. We went from just figuring out what works by trial and error, like measuring a field, to proving why something must be universally true. This jump from practical rules to abstract, provable truths, well, it changed everything. This whole move toward abstract thinking really hit its peak with one guy who would basically define our understanding of space for the next 2,000 years, a man named Euclid. So around 300 BC, Euclid writes his masterpiece, a book called The Elements. Now, he didn't invent all of the geometry in it, but he did something way more profound. He took all of human knowledge about space and forged it into a single, bulletproof logical system, all built up from the simplest possible starting points. And it's honestly impossible to overstate the influence of this book. As the historian Howard Eaves put it, it's pretty much the most widely used and influential textbook in all of history, besides the Bible. For centuries, if you were an educated person, you knew Euclid. The foundation of his entire system was this idea of the axiom. An axiom is a starting point that's so self-evidently true, it doesn't even need a proof. Like a straight line can be drawn between any 2 points. Duh, right? But from just a handful of these simple truths, Euclid built an entire universe of geometric certainty. And his system was so perfect, so unshakable, that it basically became dogma. This wasn't just seen as a useful mathematical model. For 2 millennia, philosophers and scientists were convinced that Euclidean geometry was the absolute, unquestionable description of reality itself, period. But what happens when you question a self-evident truth? Well, in the 19th century, after almost 2,000 years of certainty, some mathematicians started to poke at one of Euclid's most fundamental axioms, and in doing so, they completely rewrote reality. So this is the rule they started to question: the parallel postulate. It seems super obvious, right? If you've got a line and a point that's not on it, there's only one other line you can draw through that point that will never, ever cross the first one. For 2,000 years, this was considered an absolute, unshakable truth. But then came the question that changed everything. What if that just wasn't true? What if you could draw multiple parallel lines through that point? Or what if every single line you drew eventually had to meet the first one? What kind of a bizarre universe would that even look like? And what's so amazing is that when mathematicians like Bolyai, Lobachevsky, and Gauss actually threw out that one single rule, they didn't get chaos. Not at all. They discovered entirely new, perfectly logical geometries. These were the non-Euclidean geometries, and they described a universe where space itself could be curved. Okay, so here's what that actually means. In Euclid's nice, flat world, a triangle's angles always add up to 180 degrees. But in these new geometries, that rule just breaks. On a positively curved space, like, say, the surface of a sphere, the angles add up to more than 180, and on a negatively curved space, they add up to less. This wasn't just a new formula. It was a whole new reality. Now, at first, this whole thing just seemed like a strange mathematical curiosity, just a weird little game for mathematicians. But it turned out to be one of the most important discoveries in history because it gave us the language to describe the universe as it actually is. It turns out these broken geometries weren't broken at all. In fact, they were the key that unlocked the secrets of the modern cosmos and some of the deepest, most mind-bending ideas in all of science. Fast forward a few decades, and Albert Einstein is struggling to describe his theory of gravity. He has this incredible idea that gravity isn't a force pulling things together, but that massive objects like the sun literally bend and warp the fabric of space-time. And the mathematical tool he needed to describe this curved reality? You guessed it, a non-Euclidean geometry developed by a guy named Bernhard Riemann. And the revolution didn't stop there. It spawned whole new fields like topology. A fun way to think of this one is as rubber sheet geometry. It doesn't care about angles or lengths at all. It only cares about the fundamental properties that stay the same no matter how much you stretch or twist an object. Which is why, topologically speaking, a coffee mug and a donut are exactly the same thing. And if you look at the cutting edge of physics today, you've got wild ideas like string theory. It proposes that our entire reality is made of these tiny, vibrating strings that exist in these complex, multi-dimensional geometric shapes. We're talking 10 or 11 dimensions here. These are spaces so bizarre that Euclid could have never, ever imagined. So when you step back, the big takeaway is this absolutely incredible arc. It's a journey that started with something as simple as measuring plots of land by the Nile River, and it has taken us all the way to describing the curvature of space-time and imagining 11-dimensional universes. Really, the story of geometry is the story of our own expanding imagination. Which leaves us with one final fascinating thought. For 2,000 years, we were so sure we knew the one true shape of space, when we discovered there were others. So what new, unimaginable geometries, what new shapes of reality are still out there, just waiting for us to find them?